The higher the pressure, the lower the volume. The lower the pressure, the higher the volume. Like this. P2, P3, P4, P5. We have V1, V2, V3, V4, then V5. This is just to show that the higher the pressure exerted on the gas, the lower the volume. The lower the volume, the higher the volume, the higher the volume, the lower the pressure that has been exerted on it. So let's try an example on this. Charles' law. So Charles' law states that the volume of a fixed mass of a gas is inversely proportional to the temperature. Oh, sorry. Is directly proportional to the temperature provided pressure remains constant. Now, in this case, unlike Boyle's law states that the volume of a fixed mass of gas is inversely proportional. But in Charles' law, it says that the volume of a fixed mass of gas is directly proportional to the temperature, provided pressure remains constant. In the case of Boyle's law, the volume was inversely proportional to the pressure, then temperature was constant. But in this case, it is directly proportional to the temperature and pressure remains constant. Mathematically, we have it as V to remove this sign of proportionality, okay, pressure is constant. To remove this sign of proportionality, we have it as V is equal to K over T. Making K service of the formula, therefore K becomes V over T. And just like in the case of boys, so to have it, in case we have more volumes and temperature which are more than 1, it exceeds 1. Therefore, V1 over T1 is equal to V2 over T2. Like that to Vn over Tn. It can be represented graphical representation of Charles' law. Charles' law, something like that. So we have this, or we have it like this, where we have our volume, temperature in Kelvin, and in this case, we have our volume 0, temperature in degree Celsius. We have 273. Having understood this, we have Charles' law states that the volume of a fixed mass of gas is directly proportional to the temperature provided pressure remains constant. So I said earlier saying we have 4 variables when we're talking about experiments or calculations involving gases, and the 4 variables are temperature, pressure, volume, and number of moles. So in this variable, in the first law, which is Boyle's law, we have those 2 variables which are very effective, which is the volume and pressure. That means temperature was a constant and numbers of molecules was not included. And in this case, we have Charles' law, which brings about volume and temperature, and in this case, pressure is constant. Same thing, number of molecules is not included. And this is a graphical representation of Charles' law. So we also have the ideal gas equation. Ideal gas equation. Ideal gas equation, this is the combination of Boyle's law and Charles' law brought about the ideal gas equation, which states that the product of pressure and volume divided by absolute temperature is a fixed gas equation. So we are represented as okay, sorry, it should be general gas equation, please. Sorry. General gas equation. So general gas equation is therefore PV over T is equal to K. Therefore, P1 V1 T1 is equal to P2 V2 T2 is equal to Pn Vn over Tn. So forging ahead, we move to ideal gas equation. Ideal gas equation. So at the end of the class, I'll be taking examples each of the laws are provided, the Boyle's law, Charles' law, general gas equation. Ideal gas equation does not have any calculation. They'll move to Avogadro's law and the rest of the laws. So I just want to pick the laws at once. They will do the calculations later. So ideal gas equation has to do with the four variables. The four variables I mentioned earlier: temperature, pressure, volume, and number of mole. Note, at standard temperature and pressure, which we know as STP, the temperature of a gas is 273 Kelvin and the pressure is 1 atm. Okay, gas pressure is measured in Pascal, PA, which can also be 1 atmosphere or 760 millimeter of mercury or 1.0 times 10 raised power 5 Newton per meter square. Invariably, we can also write this as 1 atm is equal to 760 millimeter mercury also equals to 1.0 times 10 raised to the power 5 Newton meter square. And the standard volume is equal to 22.4 dm cube. So having understood this would aid us in understanding that at a given temperature, when it is mentioned as standard temperature and pressure, we have a fixed value of temperature to be 273 Kelvin, a standard value for pressure to be 1 atm or 760 millimeter mercury or 1.0 times 10 raised to the power 5 Newton meter, and a standard volume is 22.4 dm cube. Having understood that, we have this formula that relates relationship between volume, pressure, and volume, pressure, temperature, and number of moles to be PV is equal to nRT. P is our pressure, volume, number of moles, gas constant, then we have temperature. In 1 atm, 1 atmosphere, our volume in 22.4 dm cube, unknown, our temperature 273 Kelvin. To get our R, our N is equal to 1, which is the number of moles. To get our R, we have PV is equal to nRT. To make our solve the formula, we have R is equal to PV over NT. 1 atm times 22.4 dm cube divided by 1 mole times 273 Kelvin. Calculator, please. So we have 1 times 22.4 to give us 22.4 dm cube atm or atm dm cube over 1 times 273 to give us 273 Kelvin mole. Altogether, we have 22.4 divided by 273 to give us 0.082 atm dm cube per Kelvin mole. So that is the ideal gas equation, which is different from the general gas equation. General gas equation, difference is general over ideal. Our general gas equation is P1 V1 over T1 is equal to P2 V2 over T2. Then the ideal gas equation is just PV is equal to nRT, which all the values have been gotten. We have our pressure in 1 atm, our volume in 22.4 dm cube, our R, which is not given, our temperature is 273 Kelvin, our number of moles will be 1 mole, and at the end of the day, we're able to solve for our R. So therefore, our value for R here is 0.082 atm dm cube kilomole, like that. So let's start.
It's in 1979.
1979.
Question
35.
It says, which of the following statements is true?
Which of the following statements